Today we are going to see what is magnetism and its properties. The chapter is 4th in the Maharashtra State Board, and in NSCRTC book it is the 5th chapter, and there its name is Magnetism and Matter. Here we are going to discuss about the magnetic properties. So let's check. So magnetism, and it has some topics that we are going to discuss. The first topic is bar magnet and its properties. Second is current loop as a magnetic dipole and dipole moment. Third is current solenoid and equivalent to bar magnet. Then fourth is bar magnet and its dipole moment. Coulomb's law in magnetism. So obviously the magnetism works with some laws. It has to define that thing. Coulomb's law is there. Then important terms in magnetism. 7 magnetic field due to magnetic dipole. As we know, there is some dipole. There is a electrical field in the electric and current that chapter. So here we are going to see the magnetic field, which is parallel to electric field. The eighth topic is torque and work done in magnetic dipole that we are going to discuss. Then ninth topic is terrestrial magnetism. 10th is elements of earth and magnetic field. Okay, so in the gravitation chapter we are discussing about the gravitation, about two masses are attracting towards that thing. So here we are going to see the effect of its own magnetism, the earth's own magnetism. We are not discussing about some earth to move, but now we are discussing what happens on the earth with its magnetic field that we are going to discuss. And the 11th is tangent law, the properties of dia, para and ferromagnetic surfaces. Obviously the magnetism also the magnetism also has some 3 kinds of behavior that is discussed here, with the type of substances or type of matters which show the different type of magnetism. Then there is a 13th is a Curie law in magnetism. Curie is the temperature, and here the Curie temperature, above that temperature we will see that magnetism is not prominently seen, and below Curie temperature the magnetism can be observed. Then fourth is the hysteresis in magnetism that we are going to discuss. The hysteresis is a kind of loop. It's a loop, and that's when we give the magnetism to a matter and then takes out the magnetism. So the path is not going to be different. So that path we are going to discuss, and that path or loop is called as a hysteresis in magnetism. That's we are going to discuss in the, so we will see in the next hysteresis in magnetism. And this sites is created by C. Money, a principal and KV number 1, AFS Jalali West, Bangalore. So KV means Kendriya Vidyalaya. Okay. Now we will see what is meant by magnetism. So magnetism is a phenomenon of attracting magnetic substances like iron, nickel, cobalt, etc. So obviously this magnetism is observed by some metals, and those metals are mentioned here: iron, nickel and cobalt. The iron has some ores which shows itself, the lodestone shows itself a magnetism. So that itself shows a magnetism. So these 3 metals are prone to have magnetism. Prone to means they are showing the behavior of magnetism. Not every metal is showing, or non-metals are showing magnetism. This is the 3-1. Later on we are also going to discuss solenoid. So first here is this one. So solenoid also can be showing the magnetism, but that needs some external source to show it. So we are not saying what solenoid metals are there. So basically on its own the 3 metals only showing the magnetism. What is this magnetism? A body possessing the property of magnetism is called a magnet. So the body of that metal shows the magnetism is called a magnet. So that body we are calling a magnet. Next, a magnetic pole is a point near the end of the magnet where magnetism is concentrated. Obviously, so if there is some shape or the end of that material is there. So this is the end, one end, and this is the other end. This is also end and this is also end. So the material will show this side and this side, or this side or this side, as a magnetic pole. So these are the the end points will be shown as a magnetic poles, and there we are seeing the what you call concentrated intensity of that magnetism. So here it is a concentrated part, and this is the concentrated part where we can see the phenomenon of magnetism. Here the whole body, or the whole body of that magnet has some magnetism, but it will have the ends are more concentrated, not this body. That body, for if any material comes in closure of this material, sorry, that matter, the body of that magnet, that obviously they will try to stick to these ends. They will go to transfer to these ends. So they will stick at the ends only. So that's why it is saying the magnetic pole is the point near the end of the magnet where magnetism is concentrated. Next, the earth is a natural magnet. Sorry. The earth is a natural magnet. So this earth, obviously I am saying that the earth has two poles, north and south. So earth has a natural magnet available. It happens due to the core having the liquid mold made of what you call metals. So they are rotating with this liquid melt metals. So that's why even the earth is showing some kind of magnet, some kind of not. It is actually a natural magnet, and it happens due to the earth crust having this electron charge which is rotating into the core places where it is in the form of liquid melt. That's why this earth is showing, and the end points are what we are saying, that so earth is also kind of body, magnet body, and the end point is north and south is the end point of this earth. So that there these what do you call it, concentrated magnetism is present. Then next is the region around the magnet in which it exerts the forces on other magnets and on the objects made on iron is magnetic field. Okay, so the region around magnet in which it exerts forces on other magnets and on the objects made of iron is a magnetic field. So obviously iron is showing the most magnetic behavior. So iron is the element which shows most magnetic behavior. So we have discussed about earth is a natural magnet. The region around a magnet in which it exerts the forces on other magnet and on objects made of iron is a magnetic field. So when there is a body of this magnet and the region around it, the body of this magnet or having this region, and maybe this region is somewhat kind of going through that way, and drawing it again so that you can easily see. If I draw, suppose this magnet has this region and around this region, and again it is going to be this region or this region. Around this magnet, this region around the magnet in which it exerts the forces. These are the forces. These are the forces. Okay, these are the forces. They are drawing from one end to another end. These are the forces on other magnets. So if there is around any other magnet or any iron kind of thing, then they will try to attract or retract, or attract or repel those things. That object made of iron is a magnetic field. So this field, whatever they are generating around this force field, is called the magnetic field. We call it as a magnetic field. So these regions around this magnet is called as a magnetic field, where it is attracting or repelling the thing, other iron material or other magnet they are repelling. So that is called as a magnetic field. Then next we are going for Then the properties of bar magnet. Now see here, I shown you two types of magnets. One is a this one is a bar magnet. I should write it with a different color. Okay. This one is a bar magnet, right? This is a bar, and this is a horseshoe, right? Okay, this is a horseshoe type, or you can say U type. Okay, U type. There is another also dumbbell shape. Also there is dumbbell shape magnet is also there. Okay. And this both are having ends, and those ends are named as a north and south. As I mentioned, in the earth there is a north and south, and this every magnet has a north and south pole. So the north pole will be directed towards the north, and the south pole will be directed as the south of earth. So whenever you are suspending those, you know, magnets in the air with some string or some support, and they are suspended freely, able to move to rotating towards any that position, that hinge towards at that hinge, which are on which you are supporting this magnet, and freely supporting that magnet. So they are totally directed towards the north and south pole. So the ends will be directed towards the north and south pole. So that's why they are having this north and south pole direction. So each one, this will also have north and south. This one is also we have north and south. Now about this horse and shoe type, you have to hang in such a certain position that they both will show this phenomena of directing towards the north and south. That you have to understand. And later on we will discuss. But now in this chapter we are only going to discuss about the properties of bar magnet. Means we are thinking that the magnet we are considered is a bar magnet, and in respect to that we will discuss the properties of it. So the next property is a freely suspended magnet aligns itself along the north and south direction. A freely suspended magnet aligns itself along the north and south direction. This is the first phenomenon. A freely suspended magnet will direct towards the north and south. So it will give you the direction of north and south. In our basic sciences or basic whenever you primary or secondary education, you have learned this thing that people previously used compass, which has a magnet. Sorry, this is so which has a compass showing north and south, and freely suspended into a circular. This one is a compass. So it will show you north and south direction, and it is kept on the needle shape, and this and it will rotate in any direction to show you the north and south direction. So previously in while journeys or where people while traveling, they use this as this compass they will use to get this north and south directions to define where they are approaching. Next, and this why this phenomena is observed? Because of the Earth's magnetic field, Earth's own magnetic field. Because Earth is having Earth is a natural magnet, and it has a north and south pole. So these magnets will give you the north and south direction. Second point is for the properties of bar magnet. Unlike poles attract and like poles repel each other. So obviously, when you keep a north direction of any magnet towards the another magnet's north direction, they will repel each other. They will repel. They will not attract each other. And if north and south direction having the opposite poles, so they will attract each other. They will attract each other. So it is attraction. So if same direction is there, then they will repel, and if the opposite direction is there, then they will attract. Next point is the magnetic poles always exist in pairs. Obviously, every magnet is having they are both having ends, and those ends will show you the opposite direction. So here, if I mention this magnet, So this magnet having completion, the other end will be having a south. This end will be south. This end will be south, and the other magnet having this end will be north. So every magnet has south, north and south, two opposite poles will be there. They can't be separated. So if you cut this magnet, suppose if I cut one magnet into two parts, then these two parts will have, one is north, one is south. Suppose this one is north and this one is south. So if I cut it from in between, then obviously they will become north and south. So the ends will become north and south. So if I cut also, it will show you the poles can't be separated even though you cut the magnet. So the ends will always be in the opposite pairs. So this is the one phenomena. If you see in the electrical fields can be charged with a positive and negative. So one, this metal will be one as a positive available, and the other one can be available with a negative. But both at the same time, means you can observe them in the same time. You can observe the single field itself. But here you can't observe this in magnetic. Both south and north will be available in magnetic. Means in the in the substance it will be available. North and south will be available. So third point is a magnet can induce magnetism in other magnetic substances. Oh yes. So what happens if I keep this magnet for a long term with the iron rod? Okay, this is iron rod. In the environment of magnets around this, you provided some this one around this. If I provide the magnet, and this iron rod becomes the magnet, obviously. So it will accept that, and it's what you call the its internal domains will direct in the single direction, and they will become a magnet. So if there is a charge available, the charge will direct, they will align. Every charge in the magnet will get aligned, and they will show you the behavior of magnet itself. Means iron will become a magnet itself. So magnet can induce a magnetism in other substances. So induce means you are giving your property to other thing. So you are inducing that property. The magnetism is induced, magnet inducing its own property of magnetism into the another magnetic substances. The fifth is it attracts magnetic substances. Yep, the first property, the phenomenon of attracting magnetic substances. That's one in the fifth. Okay. Then the repulsion is the surest test of magnetization. A magnet attracts iron rod as well as opposite pole of other magnet. Therefore, it is not sure test of magnetization. Okay. So there is a sure test of magnetization. Okay. Suppose you kept iron rod keeping an iron rod, right? So in iron, this iron rod you are keeping, and surrounding there is a magnet. Surrounding, if you are thinking that there is a magnet. But repulsion is the surest test of magnet. A magnet attracts iron rod as well as opposite pole of other magnet. Therefore, it is not sure test of magnetization. So what happens? The iron rod on this side, if you keep north, okay, it will attract. Okay, then you remove it. Then again this side, if you keep north, again it will attract. So you might think that you are saying that magnet having two poles, right? North and south. Then why the iron is attracting on the both poles? At least one side should be opposite, right? But on the both sides it get attracted. So obviously it is the iron is showing the iron. Here we can see the iron shows the magnetic properties, but it doesn't correspond that it doesn't show you the both. It can attract to both places also. So it is not the sure test of magnetization until it own itself get magnetized. Till that time it is not showing the poles. Okay. If iron itself becomes a magnet after keeping after generating itself into aligning its own electrons into some domain, then only it will show you the north and south pole. But till that time, it's just a magnetic matter. It doesn't show test of magnetization. Okay, so both poles it get attracted. So now we are going to see the next property, that representation of uniform magnetic field. Not next topic is representation of magnetic field. So what is representation? So we will show the arrows, and these arrows will show the magnetic field, uniform field on the plane of the diagram. So uniform field on the plane of the diagram. So we think that whether in the last diagram, if I show you that here I shown you that there is a magnetic fields, okay, but we will consider only this part, okay, we will consider only this part, okay. So there we can see that these arrows are directed, okay. So on this diagram we will say that this is a uniform direction. So whenever we see here that only this part we are considering, which is might be a direction of that magnetic field, okay. So uniform field on the plane of diagram. So we will show you a representation of this uniform field will be this one. Then this one is inside, means it will show you the in the paper, means like the plane, in this plane we are showing this, we are observing like this, and so the planes, the magnetic field goes inside. So what we are observing on the screen now, the magnetic fields are going into this direction, this direction it is going. So the uniform and perpendicular into the plane of the diagram. So we are thinking this screen is as a plane. On that plane the magnetic field is going inside. The next is this one, dotted. So dotted means what? The field is coming towards me. The plane is this one and the field is coming towards me. So it is directed outward of the plane. So we can see here the uniform field perpendicular and emerging out of the plane of the diagram. You can see. So we can represent. So actually, normally we will draw this kind of diagrams. This one, when we discuss about the some phenomena in next few topics, we will discuss on that. Then only we will discuss about magnetic field. There we will see the Gauss law and the Coulomb's law. Then only we will see these other phenomena, these two phenomena. But firstly, we will think that the magnet is placed in the plane of the diagram, and with that diagrams we will show you that this uniform field or what we call magnetic field. Okay. Current loop as a magnetic dipole and dipole moment. So we can see here a current loop is here. We can see here it is entering this side and going this way. So we can see that this direction is anti-clockwise. This is anti-clockwise direction for the current entering and going out of this loop. This is a wired loop, okay. The wire is connected here and here. So this wire, through this wire the current is entering here, going this way and coming out this way. So that is anti-clockwise as I am observing here. So next what happens, this is the magnetic field. This is the magnetic field. Here we can see that it is mentioned uniform field perpendicular to emerging out of the plane. So this plane in front of me, this is the plane, and out of this plane the magnetic field is coming towards me. So how I will represent it? Okay, this is the arrow is showing that magnetic field coming towards me. Now you, for the sake of drawing, they have shown you like this, but actually the arrow is towards me and coming out. So that B magnetic field is coming towards me. B is a magnetic field direction, that is a vector. And now see what they are mentioning. This is, if you see, okay, now I will just mention it later on. Firstly I will show you. So what happened, while I am observing, the direction of current is what? Anti-clockwise. This is anti-clockwise, right? This is going anti-clockwise, coming anti-clockwise. This one. This is. So how it is showing? N. It is showing N. N means north. So anti-clockwise. If the current is flowing anti-clockwise, the magnetic field will come out, and that is showing us the north side of that loop. And if the other side, suppose if we are the back of this loop, means suppose somebody is in, I am observing this way and somebody on that side is observing that way to me, or this loop, what you will see, he will say that no, it is not moving anti-clockwise, it is moving clockwise. For them it is a clockwise. So for that person, the person who is standing opposite to me or opposite to that loop, will say that is a clockwise rotation. So the clockwise rotation like this, clockwise rotation is like this. One minute, I will draw it properly. So who were observing the rotation of this loop clockwise, okay, clockwise, so that person will say this is south, and the person who observes this loop in anti-clockwise way, so he will say no, this one is north, okay, north, okay, so north side. So I will just properly I will make it. So this one will be like this. The one who sees it as in north side, let's see, like this, north, so north pole. So the loop behaves in this way. So on my side it behaves as a north pole, on the opposite side it will behave as a south pole. So the loop, whoever observes from that side, if he sees that it is a clockwise, on that side it will behave as a south pole, and on the one who is observing it is a anti-clockwise, he will say it is a north pole. So that's only here, and the area of cross section is this one for this loop. Okay, so how much loop it is making, that area was calculated, okay, and the B magnetic field is calculated, and we can see that we can find out through that, we can find out magnetic dipole. So what is a magnetic dipole? Magnetic dipole is the area into current flowing through the coil and the number of loops made by that coil is equal to the product of that is magnetic dipole moment. The magnetic dipole moment is the current flowing through the loop having number of coils and the area A is the magnetic dipole moment. And how we can see, and what is the tip for it, when we look at any one side of the loop carrying current, if the current is anti-clockwise, the direction, then that side of the loop behaves like a magnetic north pole, and if the current is clockwise direction, then that side of the loop behaves like a magnetic south pole. So by this alphabets itself you can get the idea, here also you can get the idea, right? N, you can get the idea that it is anti-clockwise, for yes it is a clockwise way. So we can see whichever side you are observing that loop, that side you can decide which side the pole is behaving, what kind of pole will the loop will behave. That was here. The magnetic dipole moment you will calculate through this formula. It is a product of current, area of loop and number of coils. That is a magnetic dipole moment. So next we are finding the current solenoid as a magnet dipole or bar magnet. Okay, now the current loop we discussed. We have discussed the last as a topic as a current loop. So now how you can observe. So firstly I will take just a moment to say, if we draw here as a loop, okay, so this is a loop, and if we say it is a single loop, then what will happen? It is a single loop, okay, you make it multiple loop, okay, multiple loop, here also multiple loop, it is a multiple loop. So number of turns, 1, 2, 3, 4, 4 loops, it is a single loop, and this is 1, 2, 3, 4, 5 number of loops. So n is equal to 5, here n is equal to 1, it is n is equal to 4. So there are 4 loops, this is 1 loop, this is 2 loops. And what happens, this in between that maybe some kind of coil you are inserting, or sorry, some metal rod or something, on that you are revolving this taking these rounds. It might be non-metal also, it is non-metal. On that you are looping this what you call coils. This is made of, might be copper, aluminum, whatever, but these are the wire coils rotating around some non-metal. Here also this one, inside this one is some cross-sectional area of something maybe plastic or something non-metal, which is non-conductive, and around this you are rotating these loops. So this is called as a solenoid. So one side the current will go and other side the current will come out. One side the current will go, other side the current will come out. So they will behave in that sense. So if you are observing, so what happens if you observe from this side, you can see the current. Okay. So what you observe, the current is clockwise. So you will say this side is the south and the other side is the north. If you see here, you can see current is flowing this side. Okay. Observing this from this side, you will say it is north and this is south. As you can see, it is anti-clockwise. So I can say from this observation, I can see it is north, and from this here I can see south. So this is a solenoid. You can solenoid thing, solenoid loop. What we are discussing here. So these are the solenoid loops we have discussed. Now how these solenoids will behave, that's what we are going to see by diagram. Just a moment, I will erase all these things so that we can discuss it actually on this platform. So this is one. You can see that the bar is here. On this bar we are rotating these wires, current wires, and it is forming so that solenoid, this solenoid is behaving like a magnet, and that generating a magnetic field. And you can see the south is always directed towards the north. Okay, but it is internally it is directed towards the north, south to north, but outside you can see it is directed north to south. So outward it is north to south, and inward it is south to north. So this magnetic field will directing north to south outward, and inside it is directed south to north. So the whole circle will be completed here, and you can see this is the non-conductive thing on which the wire is rotating, and you can see that the current is flowing from this side to this side. So if I observe from this side, I can see the current is going this side. So obviously if I am observing this side, so current will be observed this way. Okay, this way. And from this side, if I observe, the current will be going this side. Okay, so this is clockwise, and this is anti-clockwise. You can see. So actually this is this should be dotted, it should be provided dotted, so that we can easily say that the current is going from this side to that side. No problem, the diagram has some flaws. Okay, no problem, but it should be shown from this side. If I am observing this side, I am observing, then I can find it as a clockwise, but I am observing this side, then this solenoid is showing me the anti-clockwise. So I am saying this side is north and that side is south. Okay. So one thing they are telling us that magnetic field outward is directed towards north to south. So normally inside we don't bother about, right? Inside we don't bother about, because we are not working on that. We are working on the outside fields. Okay, outside fields. So we will say north to south the direction is. So magnetic field will be running from north to south outward. Okay, outward. That's what we are going to discuss. Next is this solenoid as a magnetic dipole or bar magnet. Now we are discussing here solenoid as a remove all this name. You can see that this is total completing the loop. Okay, sorry, magnetic field is like north to south, north to south. Sorry, north to south, north to south. It is running outward. Okay, here it is showing. and the magnetic field is directed from south to north. Okay, south to north it is going. Okay, inside. Okay, magnetic field is inside, and outside it is north to south. Inside it is south to north, so south to north, and outside it is north to south. The magnetic field is running, and it is coming toward us. Okay, it is coming toward us, or not towards, I will say towards this side, because we are from the plane of diagrams, we are showing it on this side. Next, play previous and next to understand the similarity of field lines. Okay, I don't think so that is required here. So now next is bar magnet. What is bar magnet? Actually the bar magnet is a rectangular strip or rectangular prism, yep, rectangular cube, that rectangular cube which has a long length and a very small cross section, some legitimate cross section. That is the bar magnet, which has a P point. Now what this point is, that here this end, how much this end, and again I will show this another end. Okay, this end. Okay, these much ends are more concentrated. This is concentrated, and this end is also concentrated. Okay, this is concentrated. Concentrated. Okay, this is concentrated and this is concentrated. So this, at the ends, the magnetism is more concentrated. Then this magnetic dipole is directed towards south to north. Okay, magnetic dipole, and the magnetic field is outwardly. Magnetic field is towards north to south and inside south to north. So magnetic dipole is also directed from inside. It is directed from south to north. Inside is directed from south to north. Magnetic dipole. Now the magnetic length, what they are discussing is the magnetic length. So yellow line is showing that it is still only at the E, means the body of magnetic length, that is from P to P. Inside it is not, it is weak. Okay, inside in the body it is weak, but at the ends, which is the exact geographic length, the total length. Okay, the bluish is the total length. Okay, this one is the total length. This is the geographic length, but magnetic length is from P to P. Before the end, some region is there. There it is. So that is a magnetic. Inside there is body, whatever the body length is there, in that magnetism is less. At the ends it is powerful. So the first point, the line joining the poles of the magnet is called as magnetic axis. Okay, so this line, whatever the line, this joining, I will use another color. The line joining this P to P point is called as a magnetic axis, the poles of the magnet. So south and north is joined by this line, so that is called as an axis, magnetic axis. And the distance between the poles of the magnet is called as a magnetic length. So this is the P to P point, which is body of the magnet, is called as a magnetic length. Okay, and the distance between the ends of the magnet is called as geometrical length. The actual length of this metal magnet is called as a geographic length. Then the ratio of magnetic length and the geometric length is nearly 0.84. Okay, so this is the 80%. The magnetic length is 80% of geographic length. So if I say the geographic length is 100, so what is the magnetic length? It will be 84 or 80. Okay, so we can get it, that is 0.84. We will see the magnetic dipole moment. As we seen in the last slide, the magnetic dipole moment, dipole moment is m bar. I will write it again. The magnetic dipole moment is m bar, which is a product of current into area into number of loops. N is a number of coils. Okay, so that one we are going to see again with respect to this bar magnet. So what it says, that a pair of magnetic poles of equal and opposite strength separated by a finite distance is called as a magnetic dipole. So this is the separated by the distance magnetic length, and that poles are separated by this distance, separated by a finite distance, is called as a magnetic dipole. This distance actually. So the magnitude of dipole moment is the product of the pole strength. The pole strength. So the strength of this pole or this pole, south pole, that is M, and the separation 2L between the poles means 2L length. That is magnetic length. That is 2L. Okay, that is 2L. So this length is called as a 2L. Okay. Now I think so. Here I should not. This is not geometric length, not magnetic length. That is 2 length. So and the separation 2L between the poles. So that will be a magnetic dipole moment, which is equal to M dot 2L into I current. So 2L is what? 2L is the magnetic length, twice L, and which will be represented by ampere into meter square. Okay, ampere into meter square. So that is here the direction of the dipole moment is from south pole to north pole. South pole to north pole, which will go and along the axis of the magnet. That axis of the magnet is shown here. So that is ampere meter square. So here they should have mentioned ampere meter square. Okay. Mistakenly it is A dot M, but it is ampere meter square. So now we are discussing about Coulomb's law in magnetism. So obviously this magnetism works with some phenomena, that's with some laws that we are going to discuss, and that is Coulomb's law in magnetism. The force of attraction or the repulsion between two magnetic poles is directly proportional. So the force of attraction, they are attracting towards each other or repelling toward, or means pushing each other from each other, it's repelling each other from, and that is the two magnetic poles. Okay, the south north, they are attracting, north south attracting, south is repelling, north is repelling. Okay, they are going outward, so they are repelling each other. So is directly proportional to the product of their pole strengths. Okay, whatever the pole strength, that is pole strength. Okay, M, and inversely proportional to the square of the distance between them, means the distance between them, square of the distance, that is R, right? So that's what we are going to see. The pole strength is M, the distance is R, and that is the force. The force is force of attraction or repulsion between two magnetic poles is directly proportional to the product of their pole strengths and inversely proportional to the square of the distance between them. Which is, did it sound something similar to electric current? Okay, electric force. Say yes, obviously it is similar to that one, where the M1 and M2 are two poles. These are the two pole strengths is kept between some distance, that is the distance R. Yes, this is the distance R, and for the force is directly proportional to M1 M2, the force of pole strength of these two magnets, directly proportional to F is equal to F is directly proportional to M1 M2, and also directly proportional to, that is F is directly proportional to the distance. 1 minute, they have to mention it, the reverse, sorry, they have to mention it is wrong. The force is inversely proportional to the distance R square, and which we can write directly. F is equal to K M1 M2 upon R square. K is a constant. What this K means? K is mu 0 M1 M2. So K is equal to mu 0 upon 4 pi, which means that K is equal to mu 0 upon 4 pi. Is a constant, which is mu 0 is equal to 4 pi into 10 raised to minus 7. That is Tesla meter per ampere. Okay. So that is in vector form. You can write it as a F bar is equal to mu 0 upon 4 pi M1 M2 upon R square into R. R is what? R is a, okay. But what is that R means? The R means is the what is it's a unit vector. It's a unit vector. I should write it properly. So unit vector R. Okay. Here the F bar is equal to mu 0 upon 4 pi, and this one is okay, M1 by M2 upon R square, which is mentioned here. So that is the force. Coulomb's law mentions the force of attraction or repulsion, and that is this one. Now we are discussing the second property or second phenomena of magnetism, that is magnetic intensity and magnetizing force, H. So what it says that a magnetic intensity at a point is the force experienced by the north pole of unit pole strength placed at that point due to a pole strength of the given magnet. Okay, so what it means that H is equal to magnetic field divided by the permeability of that magnet. Permeability of that magnet. So it is also defined as a magnetomotive force per unit length. Okay, magnetomotive force per unit length. So H is the magnetic intensity or magnetizing force which is experienced due to the magnetic field by the permeability of that environment. Okay, so it is also defined as a magnetomotive force per unit length. Then second, it can also be defined as a degree or extent to which magnetic field can magnetize a substance. Okay, firstly now we will grasp it as just a magnetic intensity at a point is the force extended by a north pole of a unit pole strength placed at that point due to a pole strength of the given magnet. Suppose this is the north pole and it has been experiencing a force due to some outer some magnet. Okay, okay, what this north pole is experiencing, that one is calculated here. So this magnetic field is from the another material. This is B. Okay, this is experienced by this north, that, and the permeability is also a factor here. The permeability is also a factor here. Okay, so that multiplies on this north pole, that is called as H. So this north pole experiencing the H, the magnetic intensity is experienced by this M. Okay, that's what we are discussing. Now the B and U is from the different material. Okay, different magnet. Okay, it is not the magnet. Previously what we are discussing, the magnet having its own properties we are discussing. Now the magnet experiencing the properties from other one. So that's what we are calling magnetomotive force per unit length. So whatever the force he is experiencing, that we are discussing, the magnetomotive force per unit length. It can also be defined as the degree or extent to which magnetic field can magnetize a substance. So this also defines. So this property can define whether this material get magnetized or not. Okay, okay. Suppose this is just a iron rod. Okay. Now again we are giving some magnetic field in the permeability of mu, and if it is experiencing some kind of magnetic motive force per unit length, it is experiencing. So it will also get magnetized after some time. It will take some time. Okay, it is in close contact in that magnetic force it is experiencing, so that iron rod also experience some kind of magnet. So previously what we are discussing, its own property, how much it is magnetized. Now how it is magnetizing to other, that one is possible here. That one is discussed at this point. So it can also be defined as the degree to extent to which magnetic field can magnetize a substance. So this is a magnetic field. Okay, this magnetic field, and how much it can magnetize this iron rod, that we are going to discuss. That intensity can be defined here. Okay, so if the B is too much powerful, it can easily make this as a magnetized. When it is weak, then this iron rod can't be that much power. And if suppose this permeability is also too much harsh or too much favorable, then that will also affect this iron rod's magnet, whether it become magnetized or not. That will also get affected. Okay, so now it can also be defined as the force experienced by a unit positive charge flowing with unit velocity in direction normal to the magnetic field. It can also be defined as the force experienced by a unit positive charge flowing with unit velocity in a direction normal to the magnetic field. Okay, now the force experienced by unit velocity, unit positive charge flowing in unit velocity in a direction normal to the magnetic field, that can normal to the magnetic field. So its SI unit is ampere turns per linear meter. Okay, linear meter means direct, it's a straight. Okay, straight magnetic field, not something curvy or something. This is not possible, only straight magnetic field. Okay, and it is CGS unit is Oersted. CGS unit is Oersted, you can say, and this is ampere turns per linear meter. Okay, now magnetic field strength, and the third phenomena is magnetic field strength or magnetic field or magnetic induction or magnetic flux density. Now this is magnetic flux density is the number of magnetic lines of force passing normally through a unit area of substance is equal to B into mu H. See, magnetic flux. Now you are discussing of magnetic field only. Okay, but this magnetic field is not generated by the same magnet. Okay, this magnet generates B. Okay, if it is south, it is north. Okay. Going this side. So this is a magnetic field. Okay, and here one iron rod is there. Okay, now this iron rod also getting affected due to this magnetic field. Okay, so for that it is a flux. Okay, for this iron rod, this experience of magnetic field. Okay. So this is a flux. Same, it is for this iron rod, this is a flux. Okay, magnetic steel strength. You can call it as a strength also. So they, but this is also represented by B, and this is also because the same thing. It is on. This is magnet. For this magnet, this is B, and for this one iron rod, it is a flux. Okay, because iron rod doesn't have its own magnetism. So whatever it is experiencing from that magnet is called as a flux. Okay, so it is also B. And why it is experiencing? Because it is experiencing because why? Because it is hampering on it in the permeability mu. Okay, the flux. And why it is experiencing? It is because it has a intensity. So if it is intense and having a permeability, that will define B, and the H will be and you can see in the above diagram, or the intensity will be defined by the B divided by the mu. Okay, the permeability. Okay. So it is interdependent definitions of this parameters, or you can say a phenomena. So it will be defined as a Weber per meter square. Weber per meter square, and you can call it as a Tesla. So magnetic field which is experienced by other magnet is called as a Tesla. Okay. So one serious unit is a Gauss. It's a 10 raised to minus 4 Tesla. Okay, it is 10 raised to minus 4 Tesla. So magnetic flux. Okay, magnetic flux. Now here I just want to clear something. Okay, so magnetic field strength or magnetic field or magnetic induction or magnetic flux density. I need to mention this flux density. Okay, B is magnetic flux density. And now it is a flux. So in the previous I mentioned that is wrong. Just I will mention is flux, magnetic flux. Okay, this is magnetic flux. So it is defined as the number of magnetic lines of force passing normally through a surface. Suppose I define as a number of magnetic lines. Number of magnetic lines of force passing through a normal surface. Suppose this is a magnet. Okay. South to north, and this is an iron rod. Again, iron rod. Okay. The magnetic flux passing through this one. Magnetic flux passing through this one. Magnetic flux passing through this one. Okay, the magnetic flux passing through this one. Magnetic flux passing or not passing. This one is avoiding, but some way might pass through this one, and some might pass through this one. So whatever this surface is experiencing, okay, whatever this surface is experiencing, okay, this surface of this ion is experiencing, they define as a number of magnetic lines of force passing through normal through a surface. So on this surface, these are some lines are passing, that will be called as a flux. Okay. So its NI unit is Weber, and Weber per meter square is as a density. Okay, what is called magnetic flux density. Magnetic flux density density is represented by Weber per meter square, that is B, and this is magnetic flux. Actually they should have mentioned reversely, but firstly they mentioned the intensity, then magnetic density, and then now they have mentioned magnetic flux. The relation between B and H, yeah, the relation between B and H is B is equal to mu H. Okay, mu means permeability, the magnetic permeability. How now we are getting the definition of magnetic permeability, that it is the degree or extent to which magnetic lines of force can pass enter a substance. It is the degree or extent to which magnetic lines of force can pass enter a substance. So this is the possibility. It gives the possibility that how much that that force can pass through the substance. Okay, the permeability. Okay, permission. It is giving the permission. How much permeable means how much it is able to pass through that. It permits that thing. So that is a magnetic permeability. A degree to contain extent at which magnetic lines of force can pass enter a substance. Its unit is Tesla meter per ampere. Okay, or Weber per ampere per meter, or H, which is unit for what do you call it? It is the unit for this one, intensity, magnetic intensity. Okay, so how can we say that magnetic intensity? This is the magnetomotive force per unit length. Magnetomotive force. The magnetomotive force is this one and unit per length. So this is meter. So magnetomotive force is represented by H. Okay. That's what they have mentioned, magnetomotive force. Okay. So relative magnetic permeability, mu r, the magnetic, it is the ratio of magnetic flux density in a material to that in vacuum. Magnetic flux density to the material, mu is 0. Okay. It can also be defined as the ratio of absolute permeability of the material to that in vacuum. So this one, mu r is equal to B by B0, or mu r is equal to mu divided by mu 0. Okay. So mu r is equal to mu divided by mu 0. So mu 0 is the permeability of vacuum. Mu 0 is, okay, I think so. They have not mentioned what is mu 0. Mu 0 is the permeability of vacuum, and mu is the relative, and mu is the actual permeability. Mu 0 is the permeability of vacuum, and mu is the relative permeability, and actual permeability. Some phenomena for the magnetization. Now we are going to start with the intensity of magnetization. What does intensity of magnetization tells you? So intensity of magnetization is, it is the degree to which a substance is magnetized when placed in a magnetic field. The degree to which substance is magnetized when placed in a magnetic field. So it is not about a magnet, or it might be about a magnet, but when it is having a contact with another magnetic field, so how it will get affected. So it is about the magnet which gets affected, so its own property, that how much it will get affected by the other magnet. So for that thing we are discussing, for that is the intensity of magnetism, to get affected by other one. Okay, to get affected by other one, that degree we are talking, not to affect other one. Okay, so I mean to say is there, if I am going to affect the other person, then that is my magnetic intensity. If I am affecting the other person, then it is my magnetic intensity. But that I am getting affected by other person, that is my intensity of magnetization. So same here, the magnet is getting affected, how much I can get affected, that is the intensity of magnetization of that material. So next point is it can also be defined as the magnetic dipole moment m acquired per unit volume of the substance. So the magnetic dipole moment which I acquired, which that material or substance get acquired per unit volume of that substance. So it is depend on the volume of that material. So it can also be defined as the pole strength M per unit cross sectional area A of the substance. So there are three definitions: 1, 2, 3. So we can write it as I. Okay, the magnetization is I. This one. So I is equal to M divided by V. So that is magnetic dipole moment divided by V. M divided by V. And then next is I is equal to pole strength into length divided by area into length. Oh, so what happens? Magnetic dipole moment multiply by 2L divided by area into 2L. Okay. So how you can write it? M actually volume is equal to area into twice length, right? So that's what volume is equal to twice length. So it becomes it is magnetic pole strength. This is pole strength M. Okay, small m into twice which is a length. Okay. To magnetic length and divided by volume, so that is A into twice of magnetic length, which is equal to M by A small m. Okay, so pole strength divided by A, which is mentioned here. So that is the next. It can be also defined as a pole strength M per unit cross sectional area A of the substance. So next, SI unit of intensity of magnetization is ampere per meter. Ampere per meter. So it is mentioned here. So pole strength is divided by area. So pole strength is what? So if we can directly say here that it is mentioned here. Pole strength ampere per meter. How it is ampere per meter? That we can see in the another derivation. Next is magnetic susceptibility. Magnetic susceptibility. Somewhere it is mentioned like this also. This by this symbol. Okay. By this symbol also some many places it can be mentioned. So it is like some. This symbol is also used for the susceptibility. Excellent. Okay. So what is meant by magnetic susceptibility? It is the property of the substance. It is the property of the substance which shows how easily a substance can be magnetized. How easily a substance can be magnetized. So that susceptibility. Okay. So how easily it can be manipulated or how it can be susceptible. That kind of. So the material can be easily get magnetized. And how it is been defined? How it can be calculated? It can also be defined as the ratio of intensity of magnetization I in a substance to the magnetic intensity H applied to the substance. Obviously, the magnetic intensity H applied on a substance and that material itself having a I intensity of magnetization. So that how much it has a degree of acceptance to this H intensity is called as a magnetic susceptibility. So it is the ratio of magnetic, it is the ratio of intensity of magnetization divided by the magnetic intensity. So that is called as a susceptibility. Has no unit, it has no unit, right? It has no unit. So actually I should draw here what I mean to say here, the diagram which I draw here. So that diagram says that it is having itself a magnetic intensity of magnetization in the material, and outside intensity of magnetization is applied on this thing. So how much this material get affected is the intensity of magnetization and the intensity of magnetization, and how much magnetic intensity is applied from outside field is shown on this material, and the susceptibility of this material can be defined by this ratio. Okay, I by H. Okay, that is magnetic susceptibility. So relation between magnetic permeability mu r and susceptibility Xm, which can be write like this, because as in the NCERT, in the so the symbol for this one is this one, and in the NCERT it is used as this symbol. So mu r is equal to 1 plus Cm, which can be write as mu r 1 plus magnetic susceptibility. Right, this one we can write. This one also can be written as a magnetic permeability mu r and susceptibility. Okay, this is not just magnetic. This is a relative magnetic permeability mu r. R for relative magnetic permeability. It is not just a magnetic permeability. It is a relative magnetic permeability. So next we are going for magnetic field due to a magnetic dipole or magnet, that we are going to discuss at a point on the axial line of the magnet. So what we are thinking here, at a point on the axial line of the magnet. So axial line, so from one pole to another pole, the line join is called as a the bar magnet, right? The bar magnet, that is called the axial line. Okay, now we can see the diagram, and here it is a magnet. Magnet has shown, bar magnet has shown, O is the midpoint, and magnetic dipole moment is here. Then it is showing that O point distance, and the other from north pole to O point and from south pole to O point. So that is L and L. So that is total twice L distance. Okay, and outside one point is there, which is here, that is P. The point P is here, which is being get affected by the north pole also, which is affected by south pole also. So that it is kept at a distance of x. The distance for the P point from the O to P point distance is x, right? The total distance from O to P is x. So due to north pole, there is a repelling action has been applied. Repel, or the force of repel is applied on the P point, since it is getting pushed away by north pole, that is Bn, with the Bn magnetic field, and it is also having attraction of attraction magnetic field also due to S, south pole. Okay, so north pole attracts the south pole of this P, and north pole also repels or push away the north pole of P point. Okay, so P has both points, south and north, and one is attracting, one is what? Repelling. So how we will say that magnetic field at point P is equal to Bn minus Bs. So it is cancelling the Bs effect out of Bn. Okay. So it can be write as Bn minus Bs. So how we can write? Bp means at this point how much is the magnetic field, is equal to mu 0 twice mx divided by 4 pi x square minus L square bracket square. So what is the formula for P? As we know, Bp formula, mu 0 divided by 4 pi, which is equal to Q1 Q2, right? So here the M magnetic dipole has taken for both points, right, O and P, and the distance x from the O point. So O as considered as a M and P as M, the magnetic dipole moment, and divided by, and the distance is x, and divided by the distance, what you call the distance between 2 points. So that is from O point to X point. So how it is being written? X square minus L square. That is the distance. Actually, this distance has this formula. Okay. So it is mentioned here. So X square minus L square. That is equals to the force Q Q1 Q2 divided by R square formula. Okay, right? This equals to this formula, force of attraction or force of repulsion. Okay. Now next, if L is very less than X, so this L distance is very less than compared to this total distance. So this X, whatever the distance is, too much long. Then what happens? The BP is approximately equal to mu 0 twice m divided by 4 pi x cube. So what happens here? The x got cancelled by x raised to 4. So mu 0 twice m upon 4 pi x. So then at a point on the equatorial line of the magnet, second we are going to add this expression we got for this point. Now we are at a point on the equatorial line of the magnet. So the point is Q, which is placed equatorial, means that as we know from the magnet, which is perpendicular, this is perpendicular distance, and at the midpoint of this magnet we are having a Q point. We have got perpendicular distance at Q, and from that point we are trying to, at a point on the equatorial line of the magnet, we are going to calculate the magnetic field at this point. At this point we are going to calculate the BQ, or you can say PQ. So you can see, due to point north there is a BN, force of repulsion here, and due to south pole we can see the force of attraction here. Okay, on this line. So this is making obviously this is making a vector. Sorry, this is making a vector, and that you can see here, that is BQ. So intermediate vector can be calculated by Bn plus Bn vector plus Bs vector is equal to BQ. That at angle theta, how it is calculated? By the simple geometry of our 10th standard. You can see this line is straight and this one is parallel, and this is two parallel lines as we cross. So this angle, this line is parallel to BQ. So the angle of same line crossing is theta is equal to theta. So that theta angle is calculated. So that BQ is equal to mu 0 up divided by 4 pi y square plus L square divided by 3 plus 2. So where is the y? Y is the perpendicular distance from the O to the Q. Okay. And plus L square. L square is what? This L square. Okay. This is the L distance. Okay. That is L. Okay. So this y plus L square, 3 plus 2, 3 by 2. Okay, 3 by 2 y, 3 by 2. Can you explain why 3 by 2? Okay. That is 3 by 2. So if L is very less than y, L is very less, then again same way we can write y square plus 3 by 2, the by 2 is cancelled by this, and it will be remain 4 by cube. Same expression, same mu 0 twice m, but here mu 0 is not twice m. So twice m, why it came here? Because there is two dipoles are acting here, and here only one dipole is acting, right? Is it like that? So magnetic field at a point on the axial line acts along the dipole moment vector. Magnetic field at a point on the axial line acts along the dipole moment vector. Magnetic field at a point on the equatorial line acts opposite to the dipole moment vector. Okay. Magnetic field at a point on equatorial line acts opposite to the dipole moment vector. Obviously, this dipole moment is this one, and this one acting. Okay. So the dipole moment here, em bar is going this way, but the BQ is going this way. Okay. And here here in this case, if I say the dipole going this way, it is capital. potential at a point on the equator line acts opposite to the dipole moment vector. So it should be mentioned. Next we are going to do torque calculation on the magnetic dipole bar magnetic uniform magnetic field. Now we can see here is the magnetic field, okay, and here is the magnetic field, and then we have a bar which is kept across the magnetic field, and we can see there is a magnetic field which is acting with the pole strength M in the south direction this way and the north direction this way. Obviously this inside the magnet, the magnetic field always travels from I can't see this one and this one on the side, is it inside or outward, but at this moment this is a magnetic field inside that. This is the bar magnet is placed, and one is north pole, one is south pole, one is going this way obviously, and the other one is going that way generally, and the dipole moment is across the bar, okay, that is here, right? You can see it here. Yeah. So now the perpendicular drawn here, and we can see the angle of magnetic dipole moment is theta. We have drawn here. Okay. So and the magnetic length is 12. The angle which is theta. Okay. Then what is this magnetic dipole moment? I can say directly right. And this is the angle which is made by the magnetic field. Okay. So now we can see the forces of magnetic MB act opposite to each other, and hence net force acting on the bar magnet due to external uniform magnetic field is zero. So there is no translational motion of the magnet. Okay. So both are hence the net force acting on the bar magnet due to external uniform magnetic field is zero, because both are acting in opposite direction. So they both cancel each other. One will be this one added minus because in the opposite direction. So it will become 0. Okay. So there is no translational motion of the magnet. Since however the forces are along the different lines of action and constitutes a couple, hence the magnet will rotate and experience a torque. Obviously at this place this much, at this place this much translation, at this much place this much translation. So obviously however the forces are along the different lines of action constitutes a couple, hence the magnet will rotate and experience a torque. So the torque is equal to magnetic force into distance. So magnetic force is what? Into distance. Distance is what? Sin theta, right? 2 sin theta. And this is magnetic force. So this is the magnetic force mb bar into twice L sin theta, which is equal to mb sin theta. So that is mb sin theta. So again is the magnetic dipole moment, magnetic field into sin theta. That is the right. So this is how you can calculate torque. Then next we can write both all these quantities are vector. So tau you can write it like I should write like this. Tau is writing like this. Magnetic. The torque is right. Symbol for torque is like communist this one torque. So you can see here the angle. You can see here magnetic field and having angle theta with the magnetic dipole moment, and the dipole, the torque applied is also at this position, so which will act, rotate this thing, so which is perpendicular to the axis of rotation is perpendicular. Direction of torque is perpendicular to onto the plane containing. Obviously the direction passing through this one will be perpendicular obviously. So whenever that magnet will rotate like this, so the direction will pass through perpendicular. Okay, inside this magnet. So work done on a magnetic field. Now we calculate torque, we calculate intensity, we calculate magnetic field, we calculate magnetic force. So now we are coming across the work done. Work done on a magnetic dipole bar magnet in uniform magnetic field. In uniform. So we are everywhere it is uniform magnetic field. So what we are getting? Again we are getting a uniform magnetic field. We are again having a rod which is placed at angle theta 1. Then magnetic force is applied MB here which are in opposite direction. So now it rotates. You can see it rotated. So the angle changes to theta 2. Okay, the angle rotates to theta 2. Now we can see that it is the smallest difference between these two is d theta, which is theta 2 minus theta 1, right here. So the dW, the work done by this torque is called torque into d theta, the angle difference. Okay, from the first angle to the another angle. So now we can see that torque is already called as mb sin theta into d theta. So dW is equal to mb sin theta d theta. We can integrate these to get the total work done. So the integration provided here mb sin theta into d theta. Now what happens? The limit is from theta 1 to theta 2. Obviously we have changed from theta 1 to theta 1. The limit is theta 2 to theta. Yeah. So whatever happens, W is equal to mb cos theta 1 minus cos theta 2 equation will get. There, if potential energy is arbitrarily taken 0 when the dipole is at 90 degree, the potential energy rotating the dipole and inclining at an angle theta is equal to potential energy is equal to minus mb cos theta, right? So if a potential energy is arbitrarily taken 0 when the dipole is at 90 degree, so when it is at 90 degree, so you can see here 90 degree cos theta is also 0, cos theta is also both will become 0. So W is equal to 0 at 90 degree, right? Work done at dB at 0 at 90 degree. So that's why the potential energy is already taken 0 when the dipole is at 90 degree. Then P in rotating the dipole and inclining at an angle theta is potential energy is equal to minus mb cos theta. Okay. Now the potential energy can be taken 0 arbitrarily at any position of the dipole. Cos theta. Potential energy can be taken 0 arbitrarily at any position of the dipole. It is mentioned here in cos theta. Then now we are discussing about terrestrial magnetism. What is terrestrial magnetism? First, geographic axis is straight line passing through the geographic poles of the Earth. It is the axis of the rotation of the Earth. It is also known as polar axis. Just a minute, I will just check whether I am recording myself or not. Fine. We are recording also. So we will go for the site. The 13th slide. So what we are going to discuss is a Now we are going to discuss about terrestrial magnetism. What is terrestrial magnetism? Terrestrial magnetism means uh, geographic axis is straight line passing through the geographical poles of the Earth. At the axis of rotation of the Earth, it is also known as the polar axis. So we can see, now we will discuss about what is terrestrial magnetism through the geographic axis. So what happens? This is our Earth, and we practice it here. Okay. And it rotates around a point, sorry, around the line, this axis. Okay. And this is our north pole, and this is our south pole. Okay. Okay, rotate like this. Okay. This is our, they are working around this axis, axis of rotation. Okay. Through this axis it is rotated. This is Earth, and this Earth has a geographical axis, that is axis, geographical axis is a straight line passing through the geographic poles of the Earth. So through north to south this geographical axis is passing. It is the axis of rotation of the Earth. So obviously about this axis it is rotating, whether the circumferential you can see, but this axis is the only thing around which the Earth is rotating. It is also known as a polar axis. Okay, there are many names. Now I am calling it as axis of rotation, geographical axis, or polar axis. You can say whatever. There are three names there, you can say. So geographic meridian. Now what happens? Geographic meridian is what? Geographic meridian at any place in a vertical plane passing through the geographic north and south poles of the Earth. So what he is at any place, geographic meridian at any place is a vertical plane. Is a vertical plane passing through the geographic north and south poles on the Earth. Geographic meridian, can we call this one? Vertical plane passing through the geographic north and south poles of the Earth. So can we say this is the geographic plane? A plane which is passing through. Okay, this is passing through. Okay, through Earth. Okay, through the meridian means through this one is passing, right? Just cutting here. Okay. So at any place at a vertical plane passing through the geographic north and south poles of the Earth. Passing through the geographic north and south poles. It can be this way also. I can't see it now. It can be from the firstly it is the Earth. So north and south. So now I am going to discuss about a plane which is passing through all this. Okay. It is passing through okay. It is passing through. It is passing through. And here I mentioned it is passing through. Okay, so it is going through middle of the Earth. It is going through middle of the Earth, or whether it is passing. So up means north pole, it is trying to get inside and going through this one side from the south side that we are going to see. So geographic equator is a great circle on the surface of the Earth on a plane perpendicular to the geographic axis. All the points on the geographic equator are at an equal distance from the geographic poles. So obviously, if we are talking about geographic meridian, then obviously this is not. Okay, this one is not. So it is just Earth. Okay, this is An equator is a circle on the surface of the earth. So equator is a circle. What is the equator? What is the equator? You can draw it like this. So the equator, the elliptical half of the circle. Okay, equator, and this is from the same distance, yes, same distance from the north to south pole. The magnetic axis is a straight line passing through the magnetic poles of the earth. It is inclined to geographic axis nearly at an angle of 70 degree. Okay, this angle is 70 degree. This angle is 70 degree, and the magnetic, if I say this is also a magnet. Okay, this is north side, this is south side, and the axis is seriously passing through the magnetic dipole moment. Okay, magnetic dipole moment is directly passing through the axis. Okay, it is a straight magnetic axis, is a straight line passing through the magnetic poles of the earth. It is inclined geographic axis nearly. It is inclined to geographic axis nearly at an angle of 70 degree. Okay, somewhat 70 degree it is inclined. Okay, so it is not exactly on the axis of. Okay, so the axis it is making 70 degree. Then magnetic meridian at any place in a vertical plane passing through the magnetic north and south poles of the earth. So this is geographic meridian, magnetic meridian. Okay, same passing through. The magnetic equator is a great circle on the surface of the earth in a plane perpendicular to the magnetic axis. All the points on the magnetic equator are at equal distance from the magnetic poles. Obviously, then each one is 70. All these three things and these three things are 70 degree 70 degree inclined to each other, right? These three things, geographic equator is 70 degree inclined to magnetic equator, and magnetic meridian is 70 degree inclined to magnetic geographic meridian, and geographic axis is 70 degree inclined to magnetic axis, right? That's why it was somewhat just somewhat it will be a change. So that declination theta we are going to calculate here. That is the geographic meridian is here, and the magnetic meridian is here, and the angle is theta. So the angle between the magnetic meridian and the geographic meridian at a place is declination, and that place is called theta. So it varies from place to place. So lines shown on the map through the places that have the same declination are called isogonic. So this is like a theoretical part, and we have to remember. So the lines shown on the map through the places that have the same declination are called isogonic, and lines drawn through the places that have zero declination is called as an agonic line. So whenever the theta is equal to 0 degree, it is agonic, and when theta has some inclination, places that have the some declination, so it will be called isogonic declination. It is theta declination. Sorry, declination. So deep or inclination. So there is a deep and inclination. The magnetic field is drawn from the geographic meridian has an angle theta, and the magnetic field which is horizontal, and the magnetic field which is vertical to the magnetic field in between horizontal and vertical, which makes the horizontal and the magnetic field horizontal makes the angle theta with the magnetic field B. So the angle between the horizontal component of Earth's magnetic field and the Earth's resultant magnetic field at a place is deep or indifferent at that place. The angle between the horizontal component of Earth's magnetic field and the Earth's resultant magnetic field at a place is deep for inclination at a place. It is 0 at the equator and 90 degree at the poles. Okay, so when Earth is there on this this is geographical axis, e.g. here, right? This is geographical axis, and there is some here, right? Okay, firstly I will make the equator here, geographical equator. Okay, now what happens here, it is at angle 70. At angle 70, it is a magnetic axis, right? It is magnetic axis, right? It is a magnetic axis. Okay, this is at 70 degree inclined. Okay, now what it sees, the angle between the horizontal component of Earth's magnetic field and the Earth's resultant magnetic field. So Earth's horizontal component is this one, right? Earth's magnetic component GH is this, right? And the component of magnetic field and the Earth's resultant magnetic, the horizontal component of the Earth's magnetic field and the Earth's resultant magnetic field place is deep gravitational place. So the Earth's resultant magnetic field, if I draw, is B, and the vertical component is BV. And it might be, this is not B, this one, it might be this one. The resultant B is called as the, and here angle I should mention the particular delta. It's not delta, right? So the angle between the horizontal component of Earth's magnetic field and the Earth's resultant magnetic field at a place is deep or inclination at a place. So that is theta. That is inclination or deep. It is 0 at the equator and 90 degree at the poles. Equator and 90 degree at the poles. So this resultant at this position is 0. Okay. Actually, I draw it at equator, but actually equator means at the surface might be. Means to say that it is at the surface, it might be 0, not at the internal, not inside the earth. I am saying it is might be on the surface. It means to say it is 0 at the equator, at the surface, and 90 degree at the poles. Obviously, if I standing here means obviously I am at the internal. If I consider at the pole, this point is on that line. So I am standing on the axis of the magnetic field or on the geographic field. I will say it is magnetic field. I am standing here, then it is 90 degree to magnetic field. So 90 degree at the poles. Okay. Next, lines drawn up on map through places that have the same dip are called isochronic. Okay, lines drawn up on a map through places that have the same dip are called isochronic. Whether it is okay, this dip, okay, this dip, same dip, what we call isochronic. And if the lines drawn from the 0 dip is known as a aclinic. Okay, so if there is 0 dip and there is 0 dip normally at the equator, so there we can call it as a aclinic, isoclinic, aclinic line. It is a magnetic equator, at equator. And 0 degree at agonic, Lines drawn through places that have zero declination is called like an isogonic. Theta declination is isogonic. So there is a this deep orientation and declination. So theta and delta. These are things two things we have to remember. Magnetic. So now we are discussing about the horizontal component of Earth's magnetic field pH. The horizontal component of Earth's magnetic field pH that we are going to discuss. The total intensity of Earth's magnetic field does not lie in any horizontal plane. The total intensity of Earth's magnetic field does not lie in any horizontal plane. Instead, it lies along the direction at angle of d, theta to the horizontal. Instead, it lies along the direction at angle of d, delta to the horizontal. The component of Earth's magnetic field along the horizontal at an angle delta is called horizontal component of Earth's magnetic field. It's called the Earth's magnetic field. So how we can write it? BH is equal to B cos delta. So we have mentioned what is delta, which is mentioned there. So B cos delta BH. Okay, so can we go for the previous slide for the sake of this? So here it is. So it is been mentioned on the D. Okay, so BH on this delta it will be like okay on this D. So BH is equal to B cos delta. The total intensity of Earth's magnetic field does not lie on the horizontal plane, not on the horizon. Instead, it lies along the direction at an angle of d, delta to the horizontal. To the horizontal, the angle is delta, or this way, or that. Okay. The component of Earth's magnetic field along the horizontal at an angle theta, delta is called horizontal component of Earth's magnetic field. Right. So that is BH theta. Next, we are going to see B. Similarly, vertical component is B sin delta. Then such that the B is equal to the total magnetic field is equal to horizontal component plus B, and we are having its square root. Okay, so square root of horizontal component plus vertical component, square root of that is total component of the exact component of magnetic field, Earth's magnetic field. So the tangent law establishes that on the compass when north is pointed this red way and the field, magnetic field is perpendicular to this line, the P2 which is in the direction is inclined at an angle theta, that is B. So B1 and B2 component having the inclination as a B. So if a magnetic needle is suspended in a region where two uniform magnetic fields are perpendicular to each other, if a magnetic needle is suspended in a region where two uniform magnetic fields are perpendicular to each other, the needle will align itself along the direction of the resultant field of two fields at an angle theta, such that the tangent of that angle is the ratio of the two fields. So what happens? Here is two magnetic fields which are equal power, which are equally uniform and uniform magnetic fields. The needle will align itself along the direction of the resultant field of the two fields at an angle theta. So the resultant in the line of result, such that the tangent of the angle is the ratio of the two fields. Tangent of the angle is the ratio of the two fields. So the tangent, how we can say the tan theta is equal to b to the b1. So the angle, okay. So b2 is also electric field, b1 is also electric field. Both are suspended in region where two uniform magnetic fields are perpendicular to each other. Both are perpendicular. Equally, not equally powered. It is uniform. They are both uniform. Okay, but they are different power with a different intensity or different magnetic fields, but uniform nature. So that is the ratio of alpha. Comparison of diaphragm and ferromagnetic metals. Now we are comparing here diaphragm and ferromagnetic metals. So what kind of metals are available in the nature? We have discussed about our natural is a natural available magnetic phenomena. But now in the nature again some metals will show the magnetic layer. Out of that is the dia kind of, para kind of, and ferro kind of. Ferromagnetic, paramagnetic, and diamagnetic. So what the diamagnetic is? Diamagnetic substances are those substances which are feebly repelled by a magnet. Okay. So when we have any magnet near to this material, they will repel. They will not attract. They will push each other away from each other, away from the magnet. So those are antimony, bismuth, copper, gold, silver, quartz, mercury, alcohol, water, hydrogen, air, argon, etc. They will repel each other. Okay, so hydrogen, air, and water. You can see argon also there, gold is also there, silver, copper. So some metals are not even attracting; they are repelling each other. And then now, second is the para. Para means paramagnetic substances are those substances which are feebly attracted by a magnet. Okay. So they are attracted by magnet. That is aluminum, chromium, alkali, alkaline earth metals, platinum, oxygen. Oxygen. See here, water is repelling, air is repelling, hydrogen is repelling. But when oxygen which combines with the hydrogen forms a water doesn't show the paramagnetic behavior after becoming water. But okay, the actual behavior of oxygen is to attract towards the magnetic metal. Now we are going to discuss about the ferromagnetic metal. Substances are those substances. Just a moment, I have just ferromagnetic substances are those substances which are strongly attracted by a magnet. Okay, those are strongly attracted. That is iron, cobalt, nickel, gadolinium, dysprosium. These are some metals. I didn't even heard about dysprosium. Gadolinium I heard, iron, copper, nickel, and these are ferromagnetic. They are more kind of showing the magnetic behavior. So here paramagnetic needs to activate themselves. Okay, they are short-term magnetic, but ferro are strongly attracted. So what happens with the dia? When placed in magnetic field, the lines of force tend to avoid the substance. Okay, so how it will be shown? This is the way. They will try to avoid it. They will not pass through this north to south pole. They will try to avoid it. They will go outside the material. And when we go for the para, the lines of force prefer to pass through the substance rather than air. So how it will show? It will pass through the material, right? You can see it's passing through the material. Okay. It will try to pass through. Okay. Some will go outside. Okay. But if we say the lines of force tend to crowd into the specimen, okay, in the ferro, because it is strongly attracted, so obviously it will try to, as much as possible, lines of force will pass through this material. See, as much as possible. Even some materials, even which are here in the para, some are going straight. Here it is somewhat bended towards the material, somewhat bended. So as much as possible, it will attract. That is the ferro. So when placed in non-uniform magnetic field, it moves from stronger to weaker field. When placed in non-uniform magnetic field, it moves from stronger to weaker field. Okay, so if it is south to north, and if antimony is here, it will try to, so obviously it is having this field, right, going north to south. Sorry. Yes, north to south it is going. Right. And what it will, this here it is stronger field, and here this side it is weaker. So it will try to go this side, right? It will try to go from stronger field to weaker field side. So it will, this antimony, this side, sorry, this side, will try to go away from this magnet towards weaker region. So when placed in non-uniform magnetic field, okay, when placed in non-uniform magnetic field, it moves from weaker to stronger field. Obviously it will attract, so when magnet is here, north to south, and magnetic field is here, so when it is stronger and here it is weaker, so this material, if any material like what is it, aluminum, it will try to go this side. When placed in non-uniform magnetic field, it will move from weaker to stronger, and obviously it will totally attract, right? It will totally attract. I don't need to draw it right here. When a diamagnetic rod is freely suspended in a uniform magnetic field, it aligns itself in a direction perpendicular to the field. Okay. When a diamagnetic rod is freely suspended in a uniform magnetic field, it aligns itself in a direction. So you can see here the north and south poles are here. So it will try to be not close to this one, not close to the possible orientation of this rod is that it should not go on north side also, not on the south side. So it will be directly perpendicular. Okay, this is a perpendicular. It will make as much as possible away from the both poles. And in case of when paramagnetic rod is freely suspended in a uniform magnetic field, it aligns itself in a direction parallel to the field. So let's see here, it gets aligned in the direction. See, and then lastly, when a paramagnetic rod is freely suspended in a uniform magnetic field, it aligns itself in a direction parallel to the field very quickly. See, here suddenly it will try to. So it was taking slow. Here it is doing slow. It is very fast. Or okay, quickly aligns. Quickly aligns itself. Very fast process. So now, lastly, the fourth point: if a diamagnetic liquid taken in a watch glass is placed in uniform magnetic field, it collects away from the center when the magnetic poles are closer and collects at the center when the magnetic poles are further. So how you can observe this phenomenon here? You can see in the center, see, then the water tries to be when it keeps in the away. So what happens obviously at the end of this magnets, the force is very strong. The force is very strong. So what happens? They are trying to get away from this stronger field. Okay, so that's why the water is very less here, and the water is going away. Water is a diamagnetic, as you see. And when we keep this further away, this one, what happens? The water comes inside. So why it is coming inside? Because the stronger field are here. Stronger field of magnetism is here. Strong is here. So they align and try to be inside, away from the stronger. So actually they should have shown not this way, but this is what you call it. They just try to be funny and try to have experiments. That's why this one should. If you use only single magnet, what will happen? If you use a single magnet, what you will try to get away from that the end points of that magnet, right? Then if you go for the paramagnetic liquid, what will happen? Obviously, when there is a stronger field, they will try to be near the field. The most of the volume of liquid tries to be near the stronger field, and if it goes away, then obviously whatever the water tries to be towards the stronger field. Same here also, you can see the water tries to be close, and away also the same phenomenon here. For the para and ferro, the magnetic liquid behavior will be the same, and when the diamagnetic liquid is there, it will show the different behavior. So, and the fifth point, when a diamagnetic substance is placed in a magnetic field, it is weakly magnetized in the direction opposite to the induced field. Obviously, uh, when a paramagnetic substance is placed in magnetic field, it is weakly magnetized in the direction of the inducing field. Okay, so whenever you have this magnet north to south, and if you kept a diameter, so the alignment of this one, okay, the alignment of this one, if it is north, then it will tries to be north here and south this side, so it will repel each other. Okay, it will repel each other. And if you see in north and south here, the para will tries to be south here, north here. Okay. And at the ends, it will try to parameter will try to be south, so they will attract each other. Okay, towards each other. Same way here also, it will get magnetized easily. These ferrometals will try to be attract each other strongly, and they get magnetized. Substance is placed in magnetic. When a ferromagnetic substance is placed in a magnetic field, it is strongly magnetized in the direction of the inducing field. Obviously, they get induced in that same field. So the ferrometals will also show the alignments, means they get same alignment. Induced dipole moment M is small. So the induced dipole moment M is small in case of diamagnetic material. Induced dipole moment M is small, positive value. Okay. The induced dipole moment M is small, positive value. It is negative value, repelling. And here it is positive value. It is attracting. Induced dipole moment M is large and positive value. Then next, intensity of magnetization I has small negative value. Intensity of magnetization I has a small positive value. Intensity of magnetization has a large positive value. Magnetic permeability mu is always less than unity. Mu is always less than unity. Okay. Magnetic permeability mu is more than unity. So magnetic permeability is more than unity. And magnetic permeability mu is large, much more than unity. Okay. Now, magnetic susceptibility Cm has a small negative value. Susceptibility very less. Magnetic susceptibility Cm is a small positive value. Magnetic susceptibility Cm has a large positive value. They do so. Diamagnetic material, they do not obey Curie law. They do not. Their properties do not change with temperature. So for paramagnetic, they obey Curie law. They lose their magnetic properties with rising temperature. Yes. But for the ferromagnetic, they also obey Curie law. At certain temperature, called Curie point, they lose ferromagnetic properties and behave like a paramagnetic surfaces. Yes, paramagnetic surfaces. So iron loses at 727 around 727 degrees Celsius, loses its ferromagnetic behavior. So Curie law, what it says, a magnetic susceptibility of a material varies inversely with the absolute temperature. So I is directly proportional to H by T, or I is directly proportional to. So I upon H is directly proportional to 1 by T. So how it will be written? Cm is directly proportional to 1 by T. I is directly proportional to 1 by T. I is intensity of magnetization is directly proportional to magnetic intensity divided by temperature. So if I write, since if I write I by H directly proportional to 1 by T, and that's why the susceptibility is directly proportional to inverse of temperature or absolute temperature. their C is Curie temperature. So when the Cm means Cm is equal to C by T. C is a Curie temperature divided by T. So once Curie temperature has equal to T, when Curie temperature is equal to T means it becomes 1, such purity becomes 1. The Curie temperature for iron is 1000 Kelvin, for cobalt 1400 Kelvin, and for nickel 600 Kelvin. So 1000 Kelvin means yes 273 degrees Celsius, so around 727 degrees Celsius. Okay. Then what we can say here, the I intensity of magnetism is versus H by T graph is plotted, where we can see the diagram at here we can see the graph where we can see that this graph shows that you can see that magnetic intensity of magnetism becomes stable at this level, at surround. It will not increase or it will fall down. Okay. It will not increase linearly with the edge value. So hysteresis, now last topic we are discussing about hysteresis loop or magnetization curve. So what it shows that when hysteresis loop or magnetization curve means what? The magnetic intensity versus the I value, okay, versus the intensity of magnetization. What it shows that they are crossing when while going up means with the H the I increases, but when it goes opposite, when it loses its magnetization and then again regains, the path is different. The path is different. So the path, why it is different, intensity of how it differ. The intensity of magnetization I increases with increase in magnetic force H initially through OA. Okay, you can see here, okay, through OA. But what happens through OA and reaches saturation at E. Okay, at saturation point, as you can see in the previous diagram. Here it reaches to the some saturation point. Okay, this is the saturation point it reaches, and then it can be like this. So when we plot magnetic intensity of magnetization versus the electric force, or what you call intensity of magnetic intensity, we can see that through at one up to OA it will reach linearly, it will increase with the H, but when we try to reach it reaches saturation point, I will read the points directly. When H is decreased, I decreases, but it does not come to 0 at H is equal to 0. So when H decreases now, when H decreases, it will not come to 0 at H is equal to 0. When H becomes 0 here, sorry, when H becomes 0 at this point, H becomes 0, but I is not 0. The residual magnetism I set up in the material represented by OB is called retentivity. Okay, so OB, so OB, this position, at this position H is 0, but I having value, some certain value, that is called retentivity. So already some magnetization is present in that material, while the magnetic force, magnetizing force has reduced, but the intensity of magnetization is still into that material. Now what happens to bring I to 0? to demagnetize completely, opposite negative magnetizing force is applied. So what happens? So that here the negative H is applied, so that I becomes a 0. This magnetic force represented by OC is called coercivity. This is coercivity and this is retentivity. So this portion is called, okay, I will not say here, this up to this level, okay, up to this level it is coercivity. I'm sorry, retentivity. And up to this point it is coercivity. Coercivity. Okay. Okay. OC. This point. And then after reaching the saturation level D, when the magnetizing force is reversed, the curve closes to the point A and completing a cycle. So after reaching level D, when the magnetic force is reversed, the curve closes to the point A, completing the cycle. The loop ABCDEFA is called a hysteresis loop. Okay. So when you are again trying to, obviously, it becomes a demagnetized and then it reaches to D. Okay. So till this point, the I also becomes a negative at this point, and the H is also becomes too negative. Okay, too much negative. Okay, and I also becomes a negative. Okay. Now from this point we have to increase both the things, so that we have to increase the, to reach at the point we have to reach, again increase this one, magnetizing intensity and the intensity of motion, or the magnetizing force, both has to be increased to just reach H is equal to 0. We have to, or sorry, yes, to reach from here to here, we have to just make the intensity this much, and from again to reach here, to make I 0, we have to cross this much of distance. So negative H plus H to reach just I 0. Okay, here I is equal to 0, and but H has a positive value. H is a positive value. Okay. And then again it will, with the limit, it suddenly breaks the both the things, means intensity of magnetism also and magnetic force also. Now the area of the loop gives the loss of energy due to the cycle of magnetism and demagnetization, and it is dissipated in the form of heat. The area of the loop gives, the area of the whole area of this loop gives the dissipated in the form of heat. The material like iron having thin loop is used for making temporary magnets, and that with thick loop like steel is used to form a permanent magnet. Okay. For the permanent magnets we are going to use what? For the permanent magnets what we are going to use? Permanent magnet, steel. Okay. For permanent magnet, steel is used, and for like temporary magnets, temporary, here is iron. Okay. So this one is used. Okay. You can see the thinner one is called as a iron, and the thicker one is called as a steel. Animating hysteresis loop, courtesy website. Thank you. End of magnetization chapter is ended here. Now we are closing our session. Thank you. Have a nice day. Good night. Good night.